In section 9.4, we're going to be working at solving quadratic functions by taking square roots. And the key vocabulary you're going to need for this are square root and what is a perfect square. So these are things we've already discussed and should be pretty familiar to you. So when we're talking about the different possible results that can have when you're solving a quadratic function in general, but in this case specifically by taking square roots, we might have, right, so if we have x squared is equal to d, this is talking about what happens if d is greater than 0, meaning a positive number, right, equal to 0, or if it is less than 0, meaning it's a negative number. And as previously discussed, some of this information is a little bit, for your purposes, we consider it to be accurate, but in the big picture of studying algebra, it's not. So first off, every quadratic function has two solutions. So when it says 2, 1, and none, that's not entirely true. If we amend this to be finding solutions in the set of real numbers, then if d is positive, it'll have two solutions. And if d is equal to 0, it will have two solutions that are one repeated value, meaning it'll be 0, and 0 will be a solution that was found twice. So you could call it a single repeated solution, because all quadratic functions have two solutions. And if d is negative, at this point in time, you don't know how to take the square root of a negative number. But by the time you get to Algebra 2, we'll be talking about doing that. And it really has two imaginary solutions. This has two real solutions, one real repeated solution, and this has two imaginary number solutions to be fully accurate. Okay, but for your purposes, since we're only working with real numbers, we're just pretending that imaginary numbers don't exist. So if we want to go ahead, the first thing by solving by taking square roots, the first thing we want to do is isolate the square. So I'm going to subtract 11. 15 minus 11 is 4. And then I'm going to divide by 25. And once I've isolated the square, then I can take the square root of either side. Right? So then the square root of b squared is b, and that was my point. I need to solve for b. And also, when I introduce a radical on either side, I have to introduce plus and minus. Because this could be a positive number that gets squared, or it could be a negative number that gets squared to make b squared. Right? And then when we simplify this, this is going to be the square root of 4 over the square root of 25, which is 2/5, plus or minus. Right? If we wanted to see the case of a repeated solution, in this case, if I add 18 to either side, I'll get 3z squared is equal to 0. When I divide by 3, I'll get z squared is equal to 0/3, which is 0. And when I take the square root, I'll get z is equal to 0. And this is a repeated solution. Okay, so that's what it looks like when it has one solution, as the book calls it, one solution. Sometimes we're going to take, it was very convenient here that every time we took square roots of perfect squares. So 4 is a perfect square, 25 is a perfect square, 0 is a perfect square. So a perfect square is the square of a number. And when you have the square of a number, it simplifies to be an integer when you take the square root. If we don't have that, so if I start working on this problem, I'm going to subtract 5, so I'll get 3p is equal to 33. So p squared is equal to 33/3. So p squared is equal to 11. Right? So p will be equal to plus and minus the square root of 11, which is a number between 3 and 4. Okay, so we don't have a specific value. If we wanted to be a little more precise with that, and we started working with approximating solutions of a quadratic equation, If I subtract 11 from either side, I'll get 13. And so x will be equal to plus or minus the square root of 13. So what is the square root of 13? Well, we're going to go ahead and pull out a calculator for that. I know that it's a value that is between 3 and 4 because the square root of 9 is 3 and the square root of 16 is 4, and 13 lies between 9 and 16. But if I take the square root, I'll get 3.605. So we're going to have x is equal to plus and minus 3.61. Okay, sometimes we have a few more steps. Again, I want to isolate whatever is being squared. So I'm going to divide both sides by 7. 35 divided by 7 is 5. And then I'm going to take the square root of either side, plus or minus root 5. Again, this is going to be something I would, if I wanted to make this a decimal, I could, and I could give you specific decimal answers. I'm not going to be expecting that. If I add 3 to either side, I'll have 3 plus and minus the square root of 5. Now, certainly I can find the square root of 5, and I could add it to 3, and I could subtract it from 3, and have 2 decimals as my solutions, but this is sufficient as far as I'm concerned. Okay, and taking a look at solving a problem that has multiple steps, we have this situation that during an ice hockey game, a remote-controlled blimp, here it is, the remote-controlled blimp, flies above the crowd, and it drops ping pong balls. The number on the ball corresponds to a prize, so it's going to drop the ping pong ball, and then we're going to try to find out some information about that. So use the information in the diagram to find the amount of time that the ball is in the air. So when we look at this, we see that the ball's originally dropped from 45 feet. That's our starting position for the ball. And if we want to use the vertical motion model, so remember that's going to be that the height is equal to gravity, negative 16 times time squared, plus the velocity at time 0, also times the time, plus the height at time 0. Okay, so my height at time 0 is 45, so I know h is going to be equal to negative 16t squared, and at the back end we're going to have plus 45. And when we think about the initial velocity, they're dropping the ball, meaning it's stationary and then they let it go, so its initial velocity is 0, 0t. So what you find in these models is that the middle term, when you're dropping an item, is going to drop out. So when we want to look at its height, when the person catches it, its height is 17. So we're going to put that in for the height. We want to know when it was 17 feet off the ground, because that's the height that is when this guy catches it. We'll be able to now find the time for that. So we're going to do two things here. I'm going to add 16t squared to either side. I'm working on isolating the square, and I'm also going to subtract 17. So when I subtract 17 from 45, that gives me 28. Okay, and now I want to continue to solve. I'm going to divide by 16. T squared will be equal to 28 sixteenths. Now, sometimes we might want to simplify these fractions, and we can certainly do that. I generally consider that a good habit. The only reason I'm thinking maybe I don't want to do that is because the denominator 16 is a perfect square. But I could factor a 4 out of each of these, and I know 4 is also a perfect square. So if I take 4 out of 28, I'll have 7. And if I take 4 out of 16, I'll have 4. And 4 is also a perfect square. So I know that t will be equal to plus or minus the square root of 7 over 4, which becomes root 7 over the square root of 4, which is 2. So that's my time. How long is that? Well, square root of 7. It's more than 2. It's less than 3. So it's going to be a little over a second. right? So we can see that this number here is going to be, it's going to be less than 4, right? Because that would be the square root of 16. And it's less, in fact, than 3, so that would be the square root of 9. But it's more than 4, which is the square root of 2, or the square of 2. So I know it's between 2 and 3, so I know that this is going to be a number that's slightly over 1. It's going to be a little over a second. I could find out exactly what that is, but at this point I'm really not that concerned with it. So this also would be a perfectly acceptable solution where you've got radicals that are fully simplified and you don't have any irrational numbers in the denominator of a fraction.